Hello, everybody. Just doing some comparative linguistics, looking at how different languages deal with coroutines, especially as generators, and kind of is there a life cycle? So, a bit of background, a coroutine is a function that can pause itself. It can explicitly hand control back to another function. For example, in a generator, you're yielding results. And so let me just throw up some code to give you an example. And I really need to stop talking about throwing up in code. Here is a JavaScript generator. You have the function star, which says this is a little different from other functions. And inside of it yields some values. And in this case, we're pretending that we're opening a file somewhere on the file system. I wanted this to be self-contained. So we're actually pretending to open a file. We're not using nodes, APIs to open a file. What we're doing is we're pretending to open a file, then we're yielding some lines. And like good JavaScript code that holds onto a resource, we're using try finally to close the file when we're done. And as one does with generators, they fit into the iterator API. And so I can do, generate lines from a file, and I can log each of the lines. And so, what happens here is generate lines from a file. This looks like a function call, but what it's doing is it's producing a generator value. And then the first time through the loop asks for a value. And so it's gonna execute, and it's gonna keep going until it sees a yield. And the yield says, kind of makes the value available, and it pauses the function. And so, we were in this function, and then we paused, and we came back to this loop, and we logged it, and then kind of the loop needs another value. So it's like, generator, give me another value. So it unpauses at the end of the yield and continues on. And right away it hits another yield, so it produces that value, pauses itself, and so on and so forth. And when it finally falls off the end here, there's this finally clause. So when you exit from a finally clause, whether it's because you fell off the end of the try block, or because an exception was raised, or because there's some kind of local flow control, like a return statement, that all goes through the finally block. And so in this case, we log closing the file down here. And so this is an example of, a well-written generator. It acquires some resources to do its job. It produces values. And as a side effect of being asked for a value after the last one, it executes this finally statement. But do we really want resource release, closing the file, to be a side effect of asking for more values than there actually are? That's kind of, so what happens if we loop, and I'll do the same thing. What happens if we loop and, we're still going to log the line. But if, let's log the first 3 lines. If there's a letter 3 in the line, we're going to break out. We found the line we want. We don't need any more. What happens? Well, I think I have run out of space here. So let me show you, bring that in. And we opened the file as normal, we logged 3 lines, and then we closed the file. So lovely. But at no point did we run off the end of our yield line 5. So what happened here? Well, let's look at what a generator actually is. And kind of, so we've got a coroutine life cycle happening here. Something is causing the generator starts up and it's got some state, and maybe you passed some arguments in to generate lines from a file. So it's got some state, and it starts execution, and then it's in this kind of normal life cycle stage where it's yielding values. But then there's this extra life cycle stage where kind of something is telling it, I'm not going to need any more values from you, so just kind of close yourself. So I'm going to create a generator, and we can inspect what the values, generate lines from a file. And so what is a generator? Well, it's an object of type generator. And so yeah, let's look at its prototype. It's got this return function, and it's got this throw function, right? And so what these do is, if a generator is paused and you call the return function, what that means is act as if there was a return statement. You can pass it some value. By default, that's going to be undefined. When return is called on a generator that is paused, and let's get our generator in a paused state. So we're going to ask it for next, and it produces the first value. So now it's paused. So when you do gen.return, it says act as if there was a return statement right where you unpaused. And the semantics of return inside a try finally block is to jump into the finally block. If the finally block then exits normally, then you proceed to do the return. And so there's this kind of trampoline thing going on with finally. No matter how you exit the no matter how you exit the try block, you're going to do the finally block. And then if the finally block does not have its own throws or returns, then you proceed on with the kind of exit that you were doing before. And so if I do an explicit gen.return, it closes the file. And so, something about the for loop is actually, something about the for loop is causing this life cycle switch. That when you break out of a for loop, something is happening that says, I created this iterator. The for loop owns this iterator. Because of that, if we exit without using all the values, let's just tell it to return. And that's quite lovely semantics. You write a generator, you use try finally the way you expect, and you don't really have to think about how that interacts with your common looping idioms. And that happens because and I am getting ahead of myself here. I'm mucking up. So yeah, if we look at the JavaScript specification, in the semantics for loops, and apologies everybody, in the semantics for loops, if you exit a for in or a for of loops body early, it's going to cause iterator close or async iterator close. And what that does is it looks for the method return on the iterator, and it invokes it, and it does some extra checking to make sure that, we forced a return, but that forcing a return didn't do anything like a yield, which could happen if you had a try finally block and the finally block actually contained a yield statement. I think C# goes and bans that kind of thing, maybe, to avoid this kind of edge case that you have to check for. But yeah, if it's, kind of, all this extra checking is kind of avoiding edge cases where people are doing strange things inside finally blocks. But I would never do that because I'm an upstanding person. So, in this case, we close the file and we get back an iterator record that says the return value was undefined and the kind of transfer of control was a return and not a yield. So, kind of JavaScript, the JavaScript language, when they added generator functions, when they added coroutines for generators and async, they chose to put in this life cycle for generators and to integrate that life cycle into common looping idioms like for of, which means if you happen to be doing strange things with generators in library code, you should probably be aware of that life cycle and also use return or throw. Possibly, you can probably just fake that by doing a return, by actually just having a loop that goes over the iterator, but in its body just does a break, and that way you can build on the semantics of closed iterator. That's that abstract operation that's defined in the specification. Let's take a look at how another language does it, and this is kind of what prompted me to record this. It's a little bit odd. So, Python also has iterators, and let me just actually walk through kind of here's some Python. I'm going to define a method, and I've got a Python generator. Python doesn't require any syntactic distinctions on the definition of a function. You just define a normal function. The fact that it contains yield in its body is what makes it a generator. And that's a little bit of an oddity. The JavaScript folk decided, you can have a generator function that doesn't mention yield in its body. It's always going to yield 0 results, but it'll still be a generator function. And so they wanted the generatorness to be a syntactic property of how you declare the function, not of the body of the function. And Python went the other way, and that's a fine thing to do. But this is basically doing the same thing that our JavaScript one does. What I'm concerned about is I create an object, and the generator closes over that object because it needs the object to do its last line, and the last line is just going to be last line. And I can use it in Python the way, with their for in loop, which, I create I instantiate the generator, I dump the lines, and in the same way, when I hit the third line, I'm going to break out of it. And so, this does what you would expect. I'll show you that. But I can also manually drive the iterator. So I can call .next with wonderbars to get values. But what happens then? Python does not have I looked through the Python specification. Does their for in loop semantics do the same thing? And the answer is no, they did not, in fact, build any lifecycle recognition of iterators, of generators into their loop operation, but it still does the same thing. And as far as I can tell, that's because Python generators, when their reference count goes to 0, and remember, Python does not have a garbage collector in the same way that JavaScript does. It behaves very much like a garbage collected language. It's not a mark and sweep garbage collector. What it actually is it's a reference counting language. And reference counting is timely as long as you don't have reference cycles. So what Python has is it has reference counting, which simplifies the interaction between CPython and C code, the host environment. So CPython has reference counting semantics, but then it also has this cycle collector. But like a normal garbage collected language, it's, the cycle collector can run kind of whenever it wants to. And that means that Python looks and behaves like RAII. Resource acquisition is initialization. You create some object. When the code that created it goes out of scope, that object gets deleted unless there's a reference cycle. And so here, I'm going to create a reference cycle between O and my iterator. And what that means is, the reference count for the iterator decrements. I bumped up the reference count by creating it. I used it. Iterator is none. We go out of the scope of main. And so then, what happens? Oh, main finishes, but there's still a reference cycle between O and iter. There is no references to either of those. The function that created them, that held their references in local variables, it's gone out of scope. So I'm going to wait. I'm going to give myself a prompt for input. It's going to say, press enter to continue. When I do hit enter, the finally part will finally fire, but it's not really timely. And so kind of, you got this semantics in Python, which almost always seems to work because it's very rare to create reference cycles with generators in practice. But so it seems like you got all the nice properties of RAII. It seems like you've got something that's equivalent to JavaScript's integration of loop idioms with the coroutine lifecycle. And they built everything they need for the coroutine lifecycle. It just doesn't happen consistently. And it's, so Python semantics, and if you were to build a Python engine in something like Jython, well, now your timely deallocation of this imaginary file handle, the timely deallocation of that file handle depends on Jython's garbage collector firing. So, kind of the semantics work 99% of the time in CPython, but you're relying on almost RAII, but you're not actually requiring the specifications do that. So it's kind of this semantic muddle, so which I find frustrating. And so let's go ahead and see what ono.py does. Here you can see with the normal loop, I'm opening it. I didn't create any reference cycle, so right after I break, I get the notification that I'm closing it. If I print after loop right at the end of the loop, that happens after the file's closed. It's just like RAII. But when I manually drive it, I'm waiting. It still hasn't imaginarily closed the file. Now finally, the Python interpreter itself is exiting. It calls the destructor on remaining objects, and you finally, I think it was like 20 seconds I've been blabbing on. It finally closes that imaginary file. So in the margins, the semantics is not really what you want. I just find that super awkward. So anyway, thanks for listening.